Hi there, welcome to Shift Your Machine Learning Model into Overdrive with AWS DeepRacer Analysis Tools. My name is Don Barber. I am a Principal Solutions Architect at AWS, but more importantly, I'm a member of the DeepRacer Pit Crew, which means I've had the opportunity to help thousands of developers get started with reinforcement learning through workshops, public summits, and organizational events like private leagues. Super excited about today. Hopefully you've had experience with DeepRacer so far. If you haven't taken the intro session on DeepRacer, I would highly recommend you move over to the AIM 204 session and take that first. But hopefully you've had a chance to train and evaluate an AWS DeepRacer model. Got to play around with the console, configured a vehicle in the garage and whatnot, and submitted a model to the leaderboard for prizes and glory, right? But today what we're going to be doing is going to go through what's new for DeepRacer in 2021. We're going to talk about various reward function tips and techniques to get it to the next level, how to interpret those training graphs, and also finally how to analyze training graphs and models for that extra next step level of insight to make your models win. So first off, coming to AWS DeepRacer in 2021, really excited about this. We got some exciting announcements. We're now offering two divisions, both an open and pro division. With open, we're doing time trial type races with a chance to earn digital rewards, such as custom DeepRacer, shapes, paints, wraps, and more. And the top 10% of those racers will be invited to the pro division. And in the pro division, racers can earn merchandise, such as the DeepRacer Evo cars, and can qualify for the reInvent 2021 Championship Cup. In addition to that, pro racers can also participate in quarterly special events with partners such as Formula One for fun racing events with special rewards and guests. And so I'm hoping by the end of this presentation, you'll be able to shift your models in overdrive, cruise out of that open division into the pro division and qualify for the reInvent 2021 Cup. Looking forward to that. So next we're going to go over some reward function tips and techniques that you'll be able to use to improve your reward functions and train faster, more consistent models. Just a quick little reminder, here's a really basic reward function. Parameters are submitted as a Python dictionary. We see that in the first line of the function definition here, and with all kinds of information available, and we'll go into that in depth in the next slide. But you can see in this particular example here, we use two of those parameters. One is track width, the other one is distance from center. And reward based on that basically is it within 25% of the track width, or within 25% of the center of the track, and if so, give it a reward. If not, give it a low reward or a punishment. Here's a list of all the parameters available to you as a developer in that dictionary. Full details are available in the AWS DeepRacer documentation. You can see a link there at the bottom. And what's really important to note here is that the neural network is only making its decision not based on this data. The neural network is making its decision based on the data coming in from the sensors, right? In the case of the original DeepRacer, that camera, or the case of the DeepRacer Evo, the stereo cameras and the LiDAR sensor, and using that information, making its decision. Then your reward function runs and has access to all this other information available to it. So you could come up with all kinds of interesting strategies. Everything about where the car is, what the car is doing, the size and shape of the track, and and any other objects of the track. So you could reward that neural network in the decision it's made with all this other information available to you. So what we're going to do now is go through a couple of these parameters, and that are often overlooked by developers that could be really, really useful. And so the first one of those is steps. Steps are often overlooked, but when combined with progress, it's a really easy way to reward for getting further along the track for the same amount of time. And just reiterating what a step is a single iteration of the loop you see on the screen. So image comes in on the sensor, that's the state being passed into the neural network. The neural network makes its decision, it chooses an action and performs that action. And then what ends up happening is your reward function then runs. It actually says, hey, that was a good decision or that was a bad decision. And each time that loop runs, which is about 15 times a second, that is a single step. And how do you use that? So, here we can see how useful steps can be. On the right, on that bow tie track picture there, we could see a fairly straightforward follow the center line, model. But then adding a reward function for progress over steps, so you can see that bit of code at the top, we get something that looks like the track on the right, where it's actually learned to cut off the cut to the inside of those turns, and actually cut significant time off of its total time on the track. And of course, getting closer to that optimal racing line that we're all after. And so while we're here, I do want to show another interesting way to maybe visualize your reward function. So you could see this exact same reward function that we just showed, but what we're doing is we're graphing the result of that reward function against the two parameters. So when you have two parameters coming in here, one is progress, the other one's steps. So you see those graphs graphed on the x-axis and the y-axis, and then the output is basically how much of a reward it's getting. We could see it goes from a low reward is dark blue to a high reward is bright yellow here. And what's going to happen is the neural network is going to learn over time. It's going to try to locate itself in the bright yellow parts of the graph here. So you can see here what's happening is the reward function is going to find that spot at the upper left of the graph here, where progress is high but steps are low, and that's exactly what we're going to see is going to reward, and exactly what we want out of this thing. So if you're ever having trouble sort of figuring out if your reward function is actually going to be rewarding on the right thing or not, do definitely recommend just graphing it. Might get sort of complex with multivariable graphs. You might have to go to 3D, even 4D graphs, but a super powerful way to help visualize what's going on there with your reward function. So another useful input parameter is waypoints. Oftentimes developers sort of dismiss waypoints, but it can be a super powerful way to change what your reward function is rewarding upon, depending on the region of the track that the vehicle's in at that time. So for example, if you look at this track, the reInvent 2018 track, we actually want different behavior at different regions of the track. So at that straightaway at the bottom, we want to go really fast, but leading into that first turn, we want to go into it starting on the outside. As we move into the middle of the turn, we want to be on the inside, and then as we leave the turn, we want to be accelerating as we exit the turn. And using waypoints, we could actually set the reward function to reward on those different behaviors. So to dive further into that example, just look how this code will reward. We have a little bit of a zoom in on the reInvent 2018 track here, and what we're going to do is actually pick out the waypoints that determine the behavior that we want. So we can see here as we're going into the turn, that corresponds to waypoints 5 through 9 here, and as we're in the middle, coming into the turn, in the middle of the turn, that corresponds to waypoints 10 through 20. And we can see exactly what we're doing here in the reward function, where if you're between waypoints 5 and 9, I'm going to reward if you are on the outside of the track, the right side of the track. Whereas if you're between waypoints 10 and 20, I reward if you're on the left side of the track. And so really keep this technique in mind as you dive into the further analysis techniques, because what you might find is you identify specific parts of the track that just need a little bit of tweaking, compared to the rest of your reward function. And so using the waypoints with a little if statement there can really help sort of pinpoint behavior of the reward function. And in case you're wondering, how to obtain the waypoints, how to visualize those waypoints, we'll go over that in a couple slides when we get into the log analysis notebook. But while we're on the subject of waypoints, I do want to recommend making use of some of the modules available to you in AWS DeepRacer for your Python reward function, specifically the NumPy, SciPy, and Shapely modules. They make some of this math really, really easy. So you can see in this example here that we're loading the waypoint into the Shapely linear ring object. And using that, we could actually do some very simple calculations on things such as distance to that center line of the waypoints with other objects. So in this one here, we can actually point out we're taking the first object and calculating how far it is from that center line. If you weren't using these Python modules, you would literally have to loop over every single waypoint and do a bunch of geometry and trigonometry to figure that out. So take advantage of those because they're there and they're super, super helpful. And speaking of geometry and trigonometry, it's pretty often that developers want to implement rewards based upon distance and angle to waypoints. So here's just a basic reference to that high school math. If you want the distance between a car and a waypoint, use Pythagorean's theorem. You could see it here. But if you want the angle between a car and a waypoint, use arctan. Little point of caution here is that if the waypoint is actually closer to the origin, the x and y coordinate of 0, 0, what's going to happen is those two distances are actually negative. So those two negatives divided out are going to end up being a positive and make the angle look like it's in the opposite direction. So for that reason, just about every standard math library, including Python, has an atan2 function that takes that into account. So very much use the atan2 function when you're doing angle math with DeepRacer. And just another point of warning there is that it will return the answer in radians, whereas the parameters dictionary that's sent to you, things there are in degrees. So the heading and steering, for example, are in degrees. So you just need to convert one to the other. It's pretty simple, multiply by 180 over pi before comparing that. Another thing to keep in mind is if the car is heading straight for the y-axis, you will have a heading of 180 degrees. But if it just makes a real slight shift to the left, it will actually swing all the way around to negative 179.9 degrees, right? So that's going to look like it went completely 360 degrees in the wrong direction when it really only went, a tenth of a degree in the correct direction. So just keep that in mind as you're doing your angle math and whatnot and your reward function. So hopefully you found some of those reward function techniques, compelling, and we'll be able to use those to improve your models. But sometimes developers want to know how their training is going and look to the training graphs that you see in the console to get a sense of that. And so in this section, what we're going to be doing is going through several training graphs and starting to get a sense of how to interpret those graphs. It's really important here to keep in mind that there's a bit of an art to machine learning. There's definitely a huge amount of science involved, don't get me wrong, but some of these interpretation, you're trying to sort of decide what's going on inside of the neural network. And the analogy I like to use is it's a little bit like a brain scientist trying to figure out what's going on inside a human brain by attaching electrodes and measuring the electrical output while you're thinking about different things, right? And a little bit of like that's going on here, where we're going to be sort of seeing what's happening from the outside and making an educated guess, a little bit of an artful guess there on what's happening inside. But it's a really important skill for an aspiring machine learning enthusiast. So let's just dive right in. So first, a quick little tour. The green line is the average reward function, given by the reward function over time, whereas the blue and red lines are the completion percentage, how far the car actually gets around the track during training and evaluation, respectively. So note the scale on the left is the reward graph scale. It is variable, so that will change as depending upon the range that you actually choose to reward on in your reward function, whereas the scale on the right is fixed between 0 and 100. Every so often we have developers ask us, well, what's it mean when my reward graph goes above or below my completion percentage graph? And really it doesn't mean anything. They're completely independent scales, so don't read too much into that. Now, for this particular example that you see on the screen here, we could see that there's been about 600 iterations, which is not too much, and the graphs are still going up. The evaluation completion percentage just reached 100%. It's not solid there; it's still jumping around a little bit, but the training completion graph is still has a ways to go, but it's still trending up. So, I'd basically say this reward function and model is showing a lot of progress, but it's not done yet. I would just give it more training time. So whoever's done this one has done a pretty good job, actually. Want to digress just real slightly here. Just talk about, common question is why are the training and evaluation lines separate? So I'll talk a little bit about what's actually happening under the hood here. The training graph is the performance of the vehicle, while experience is being gathered. So it's trying different things. It's basically exploring its environment. It's a little bit of randomness. Basically, it's saying, hey, what happens if I do this? What happens if I do that? It's sort of exploring and just gathering experience. But once it gathers enough experience in sort of this batch, it's going to go off and basically analyze that batch and basically do a bunch of math and try to maximize what it's doing and adjust the weights and biases there. But while it's in the background, sort of analyzing that math, the environment's freed up, and what's going to happen during that is an evaluation is run. And the evaluation is not doing exploration. It's literally just saying, do the best job you can from everything you've learned up to this point and go. So it's not going to try random things. It's just basically just going to do the best job it can with what it's already learned. So for that reason, that's often why we see the evaluation graph higher than the training graph, just because it's not trying out different things. It's literally just trying to exploit what it's already learned. So that's why those two graphs are separate. Moving back, we'll just go through a couple more examples here. This one's good. What we can see here is that the percentage completions haven't gone north of 15%, and we're up at like 6,000 iterations. And the reward function is sort of jumping all over the place, but not really improving. So, this is not a good sign at all. And what I would say is probably happening here is the reward function is not rewarding on anything that's actually helping the model to get better, actually get around the track further. So I would strongly consider throwing away this function and starting over with something else, or at least heavily modifying it to do something more akin to learning, to actually help it actually learn to get around the track a little bit better. And the next one's on overfitting. So, overfitting or overtraining is like a really important concept for machine learning. With traditional machine learning, the problem is that the neural network learns everything there is to know about the training data set, but can't take anything else. So basically, if you ask it something, maybe close to the data set, but not in the data set, it might give you a really, really far off answer and basically make it useless for anything except for the data it was already trained on. With AWS DeepRacer, where this normally comes into play is that it's overtrained, it's trained on a specific track for too long. And a good model should actually be picking out the features of the road. It should be looking at the center line and the side lines and saying, hey, these lines are going to the left, therefore I'm going to turn my wheels to the left, right? But if it's overtrained on a track, it might actually pick out something else. It might actually say, hey, when I'm at this spot on the track, I always see the background angle between the wall and the grass looks like this. So therefore, every time I see an angle that looks like that, I'm going to turn to the left. The problem with that is that it works great on that one specific track. If you were to do an evaluation on that track, it would run beautifully. But if you try to run that on a different track, or even the same track in slightly different conditions, like you go to a physical summit and there's the same track there, but slightly different lighting, or maybe the barrier is 3 inches further away or something like that. It's not general enough, and basically it won't know how to operate and will do very, very poorly. So we're really trying to avoid that with AWS DeepRacer. So in this particular example, we could see that our evaluation completion percentage hit 100% a long time ago, and we just got there with our training completion. So at this point, I would actually say this is a pretty fully trained model, and we should actually stop this. If we actually train this much further, there's a real risk of overtraining this. If for some reason I wanted to do more training, like perhaps I wanted to shift my reward function from training on just getting around the track to getting around the track faster, what I would actually strongly consider is actually running this on a different track, like maybe switch it from the reInvent 2018 track to the Bowtie track or something like that. And that's a really valid strategy, actually, is just running on different tracks, maybe an hour on this track, an hour on that track, and an hour on that track. And that way, the training is never run on the same track long enough to actually sort of overfit to just that track. And you sort of force the model to learn the feature, operate on the features of the road instead. Next one, this is a big thing. So lots of developers sort of over-index focusing on hyperparameters. And here's the thing: is the hyperparameters, the default hyperparameters are really, really good. We put a lot of thought exercise into setting those. So it's fairly rare that the hyperparameters need to be adjusted. So we see developers do this a lot, where they focus on hyperparameters instead of focusing on their reward function, which would actually is probably where they should be focusing. But every so often you do get to a situation where it does help to adjust your hyperparameters. And you can see in this particular graph right here, we see the training graph and the reward function sort of ricocheting up and down. And it's not, again, there's an art to this, but that's a sign that maybe the learning rate is actually too high. What will actually happen is the optimal value for your weights and biases inside your neural network might be a certain value, and your learning rate is actually swinging past it. And on your next iteration, it's actually swinging below it and isn't actually able to get there. So it might actually make sense to pause training and start it up again with a lower learning rate here. So something to consider. Pretty rare, but definitely something that you might see come across in the graphs. But so hopefully you got a good sense of how to interpret those training graphs from the console. But what if it doesn't actually catch the information you're interested in, or demonstrate the information you're interested in? So for example, we saw a completion percentage around the track, but what if you are actually interested in how fast the car is going? So if you have a slow car getting around the track all the way and a fast car getting around the track all the way, well, the fast car is still going to win the race, right? So you might be a little bit more interested in that kind of thing. So how do you pull out that information? And that's where we need to actually dive into the training logs. So we do make the training logs available to you. You could download those and process those. And what we could see is that, so here's an example single log entry. And a typical log file will have thousands of these lines. And there's going to be one for every single episode and step. Just a quick reminder, an episode is basically a lap. So you start at the start line and you make it all the way around the track, or you start at the start line and go off the track at some point. That is a single episode. And again, a step is that sort of iteration loop where the image is coming in, the neural network is making a decision, it's executing that decision, and then your reward function is running. So in this particular example, you could see, episode number 619, step number 44, the car was at 2.958 on the x coordinate and 1.096 on the y coordinate, plus a variety of other information available, such as the steering angle, the reward, your reward function returned, its speed, etc. So you could basically process these logs and pull out all kinds of insights. So several ways you could process that log data. One of the most commonly used ones is the one available at this link at the AWS DeepRacer Workshops GitHub repo. So what I've done is I've trained up a model using the 2019 Championship Cup track and run an analysis using the log analysis notebook at this repository. And I'll show you some of the results from that now. One of the best things about this notebook is it makes it a really, really easy way to visualize the track and the track waypoints. So you can see here, this is the reInvent 2019 Championship Cup, and we can see all the waypoints between 0 and 153. And we can also see on this track that the waypoints are fairly close together, and they're fairly evenly distributed. That is not true of all the tracks, so it definitely helps to look at the tracks and see where the waypoints are. And that comes in really useful in our reward function as we see we need to tweak it in certain areas. What does happen in the notebook is it actually does group those episodes together because there's several hundred of them. It might get sort of hard to visualize seeing all those points. So it does group them into iterations, groups of 20. That is configurable, but it does make it a little bit cleaner to look at the graphs. But if we look at the graph right here, we could see this mean reward, which is the same as that green line that we saw in the console graphs. So we have that, but we also have this additional information available to us because we literally have access to the raw data now. So we could see here the deviation of reward is also going up over time. And if we look at the actual scatter plot, we could see it's all over the place. So even though that average is going up, if we were to actually run this model, we could see that, several runs are going to do really well. They're going to make it all the way around the track probably. But every so often, you're going to get ones that just don't do well. So if I was to look at this graph, I would actually say, you know what, that scatter plot's really all over the place. I want to do some more training until I sort of have this consistency, this more consistent model where most of my points are in that upper right coordinate, part of the graph. And I basically am confident that every single run I'll do pretty well. Another interesting part of the log analysis notebook is a heat map. We actually see where the vehicle is getting rewarded on the track. And you can use that heat map to identify if the car is getting rewarded for being in the wrong spot. In this particular example, it's pretty good. It's following the center line around. But maybe I want to tweak this a little bit just to get that little extra edge on my race and see, maybe at that bottom S-curve there, I want it to go straight through the track instead of following the center line so well. So what I might do there is actually go to my waypoints and pick out, for this range of waypoints, I actually want it to be on the inside of the track or the outside of the track or the left, right, or the left side or the right side, and then reward slightly differently there. Put that little if statement inside of my reward function. One thing I do want to point out, though, is that this particular heat map doesn't show, it just shows where the network is being rewarded. It doesn't actually show what it's being rewarded for, or if it's actually being rewarded for the right thing. In order to get that, what we actually need to do is actually dive into the rewards for every single action. So the notebook does have this mechanism where we actually see the action distribution for every single node in your action space. So if you have, let's say, 9 different possible actions defined in your action space, you'll actually see this graph 9 different times. This particular one you see on the screen is for an action saying go straight at 0.33 meters per second. You can see that in the upper right where it says ST0, SP0.33. And what we can see is every spot around the track where that specific action was rewarded. And what's very interesting is even on that sharp turn between waypoints 82 and 93, which you can see the little flags there, it's being rewarded for going straight. Why is it being rewarded for going straight on a sharp left turn? That's something that we might want to look into and maybe put a little if statement in there to not reward on that. But it also picks out some other interesting things. So this is the exact same training run, but for a different action. This is actually 30-degree right turn at 0.33 meters per second, and we can see it's not rewarded at all. Why is that? It happened to be that my reward function on this run actually punished if steering was over 15 degrees. The intent there was that you get to a more optimal racing line if you don't have to turn your wheel that sharp, and you basically plan ahead and start on the outside of the turns and whatnot. But on this particular track, that's probably not a very good strategy. There's a really, really sharp left turn there, and it's going to have to turn sharp to the left. It also sort of says, why do I even have a node in my action space for a sharp turn if I'm never going to reward on it? I'm basically wasting a bunch of training math on an action that I'm never going to use. So using these graphs, you could actually sort of pick out the discrepancies between your action space and your reward function and maybe make adjustments for the future from there. And finally, we come to one of the most useful parts of the notebook, in my opinion. The notebook has over 900 sample images that you could feed into your neural network and see exactly what that neural network, what decision it would make in that situation, and also what it's looking at to make that decision. So a couple examples here we could see on the left. This is a great example right here. So there's a outer line to the left, and it's focused right on it. You can see that heat map is really, really bright, and the neural network is going to look at that and say, wow, I'm about to go over that line. I really need to turn to the left here to not do that. The middle one's a little bit questionable. That's you could see a hot spot sort of in the middle of the track, really nothing there. Given this, nothing really alarming about this one, just a little bit suggesting that maybe I need to train more. So it's a little bit more certain what happens in this type of situation. I could maybe see something where it probably goes off the track a little bit more around this part of the track. So probably just need some more training in this type of environment. And the one on the right is actually really, really concerning. Yes, there's a little bit of highlight on the center line and outer line, but more worrisome is the very heavy focus on the grassy area and the wall and the angle between the grass and the wall we see there. So this is a big sign that this neural network is actually getting overtrained for this track environment. So what I would do is basically either back up to an earlier version of this model or actually maybe train it on a different track to try to get it to unlearn this behavior. So definitely something to take a look at there. So hopefully now you've learned some new reward function techniques, seen how to interpret training graphs and dove into some of the additional insight available through log analysis. So I want you to be able to, shift your machine learning model into overdrive. Check out these links for the log analysis notebook, some more tips and tricks. Look forward to seeing you all on the track and encourage you all to take use of these new skills to make it from the open division out to the pro division and hopefully see you at the reInvent 2021 championships. Thanks so much for your time. Really appreciate it.